Renyi correlation.
Thank you for having me here. I am Farzan Farnia, and I'm from Stanford. So today, it's my honor to give a talk about principal minimum Renyi correlation from marginals to joint distribution. So this is a joint work with Meysam Rezabian, who is a postdoc member in our group, Shiram Kannan, a former postdoc in our group, and now is an assistant professor at the University of Washington. And it's supervised by my advisor, Professor David Shea. Okay, so let me start with this genome-wide association studies example. So here we have this data set. It's a data set that we know the SNPs and genome sequence for, let's say, 1,000 individuals. So we are working with a high-dimensional setting. The number of SNPs is something 3 million. And now the question that we may ask here is that how to model this data by a joint distribution. So one may say that we can estimate the joint distribution through the data set, but it's not the right approach because the number of SNP sequences is 3 to the 3 million, which is so large. It's basically infinity. Okay? So an approach to do this is we can find some lower than marginals from the data. So we can estimate them reliably, and then we go through this step and find the joint distribution, estimate a joint distribution that agrees with these lower than marginals and represents our data for modeling goals. So our focus in this talk is on this step from lower than marginals to joint distribution. We want to study what's the right way in order to find the joint distribution from these lower than marginals. Okay, so for an unsupervised learning setting, we can have this principal maximum entropy. Basically what it says is to pick the distribution maximizing Shannon entropy subject to this distribution lies in class C. So lower than marginals will characterize a class of joint distribution C agreeing with these lower than marginals, and then we'll solve this optimization problem and we'll have a joint distribution P. Principal maximum entropy tells us to pick the one that we have the most uncertainty under. So it's the least committed distribution that we can have here. Okay, now let's change this example a little bit. Here we add a trait y. Let's say we want to use this data set in order to predict this y. So this y can be diseases type of traits like breast cancer, no breast cancer, or even non-diseases type like handedness, whether we are left-handed or right-handed. So in this case, we can see that it's more sensible if we want to use the philosophy of principal maximum entropy to define a dependence measure and minimize this dependence measure between x and y on all joint distribution that lies in class C, the class C that satisfies our lower marginals. So basically, the reason is that here the role of y is different from the role of these xi's. So we want to use these xi's in order to predict y, and when we maximize joint entropy of xy, we don't consider this difference between their role. Okay, now the question that we may ask is which measure of dependence to minimize. So in the last slide, we have a general measure of dependence, D. Now the question is which measure of dependence that we can minimize here. So the one that would be suggested by Shannon entropy is mutual information. And it's in fact the subject of this 2004 work by Glauberson and Tishby. And the issue with this mutual information is that we don't have, there doesn't exist any efficient algorithms that can find the distribution minimizing mutual information. So for its computation, we have some problems. So we thought about other measures of dependence. One can be Pearson correlation coefficient. It's the most well-known one in statistics and most well-known one in almost all fields of study. But the problem with Pearson correlation coefficient is that it's not label invariant. If you change the labels, the value of Pearson correlation coefficient would change. So Renyi, observing this issue, he suggested this metric, Renyi maximal correlation, and this metric is to take the maximum of Pearson correlation coefficients over all functions fg that we can define on xy. So in this way, we can address nonlinear dependencies between xy, and it can be seen that this measure that find the two F and G's that maximizes the correlation of these two under this function will satisfy several properties, several desired properties. So the first thing is that it's between 0 and 1. It takes 0 if and only if x and y are independent, and it would be 1 if there exists a function of 1 to be equal to the other. And last is that Renyi correlation between two jointly Gaussianly distributed random variables would be equal to their absolute value of the Pearson correlation coefficient, and is consistent with the fact that once two jointly Gaussianly distributed random variables become uncorrelated from each other, then they are independent as well. So now, based on these desired properties, we ask what about principle of minimum Renyi correlation? So now we pick the distribution P that minimizes Renyi correlation between x and y under this distribution. So we want to solve this optimization problem. So we have to address two things about this optimization problem. First, the analytic structure of the minimizer. So we have to see what kind of structures are there in the distribution that minimizes Renyi correlation. And second is the computation. So we need some algorithms to compute the distribution minimizes Renyi correlation. First, let's start finding the distribution minimizing Renyi correlation for a rather simple case. We change to the continuous case in order to have some intuition about the structure of distributions that minimizes Renyi correlation. Here we have real valued x1 to xp and y. We suppose that we are given first and second order moments. So for this vector xy, we are given this mu and lambda, the first and second order moments. And now the question is, in this class of distribution, what is the one that minimizes Renyi correlation? And the answer is, it's not hard to show that jointly Gaussian minimizes Renyi correlation in this class. So it's simple to show that it happens. If we go over the proof, the key property of jointly Gaussian that helps us to prove this result is the linearity of conditional expectation. So this linearity, this structure, helps us to prove this result. Now we ask, is the same thing holds for the discrete case or not? So let's shift to the discrete setting. Here we have discrete xi's without loss of generality. Suppose it takes on values in this set 1 to m, and we suppose that y is a binary trait, as we had in the GWAS setting. So it's what we suppose here. Now, instead of moments, let's say we are given second order first and second order marginals, equivalently second order marginals. And they characterize a class C of distributions that agree with these given margins. So we have pxi xj and pxi y's for all values that we can define on xi and y. And then, using the same structure, it's not hard to show. If we suppose there exists a distribution in this class C with this separable structure, then that distribution will minimize Renyi correlation. So under the existence of this distribution, we know that this distribution will minimize Renyi correlation, and the minimum value would be achieved by separable functions fg. Just recall the definition of Renyi correlation. Now, let's say we suppose that there exists such a distribution. Now I want to provide you with the recipe to find the conditional distribution y given xi. The recipe is that we shift to indicator variables. So we have this vector x, and we build this vector of indicator variables like this. So as an example, here we have this x1 for individuals in the GWAS setting. We shift to these indicator variables. You can see the connection between here. And now, having this vector of indicator variables, I find the minimizer z star to this optimization problem. It's basically a quadratic optimization problem, and these q and f's entries are just based on the pairwise marginals. So it's basically a linear regression on indicator variables, as you see here. So we do this linear regression, define h like this, It's a separable function. And now, if that P with separable conditional expectation exists under that assumption, the conditional distribution of y given x would be exactly this H. Okay, so far, we've supposed that there exists a distribution with this structure, with this separable structure. Now the question is, under what conditions it may exist? So from here, we can find a necessary condition. The observation is that this probability is between 0 and 1. So this H should take values between 0 and 1 for all x's. So even if we do not suppose P with separable conditional expectation exists, in order for that P to be exist, this condition should be satisfied. Now, this is a necessary condition. The question is whether it can become sufficient or not. And the answer is yes. So how to check whether this condition holds? We start with that recipe. We find a minimizer z star to this optimization problem. And then we form this H. If for every x1 to xp, the value of this H is between 0 and 1, then this is a necessary and sufficient condition that that distribution exists and we are in the fine regime. Okay, so let me repeat it again because it's the takeaway message. So we have here a necessary and sufficient condition under which we know that the distribution that minimizes Renyi correlation have that separable structure, and under this assumption, we can compute it efficiently, unlike the case that we have in mutual information. So one may complain that checking this condition would take an exponential time, but it's not. Since we have this separable structure on H, we can check this condition in a linear time. And it's just because of this separable structure that we've observed in this H. Okay, so far we've discussed this separable structure, under what condition it may exist, and what happens if it exists. But what we didn't specify for how many distributions it may exist. So consider this diagram. We have a ground truth distribution Q we are not aware of. Then I estimate second order marginals Qxi, Xj, Qxi, Ys. And from them, I form a class of distribution CQ. Now the question is, how large is the subset of Qs for which this CQ satisfies that condition, under which we are in the fine regime? The best thing that so far we have proved is that for P uniform, there is an epsilon, such that for any Q in the epsilon distance, so it's a norm one distance, in epsilon distance from P, CQ contains a distribution that has that separable structure. So the measure of the subset of distributions that it would be satisfied under is not 0. The probability is not 0, but it's the best thing we have proved. An interesting question is, can someone prove a result better than that or not? Okay. So far we've talked about just the structure, how we can find the distribution minimizing Renyi correlation. Now let's see an application. Here we have variable selection problem. Let's say we want to select variables based on this optimization problem. So we maximize Renyi correlation between those variables selected and y based on this constraint that the number of variables should be less than k. Okay? So our work proved this lower bound for Renyi correlation, and we know that it can become tight under the additive structure assumption. So we have this lower bound. So one may say, instead of having Renyi correlation here, I may maximize this lower bound, which can become tight. Now, the result is that it's the same as group LASSO when you make an empirical average, when you do a maximum likelihood estimation of the pairwise probabilities of the distribution. So it would exactly result in this optimization problem. And it's group LASSO. So it's a justification for group LASSO using the principle of minimum Renyi correlation. Okay, so it's just an application. So in this talk, I introduced principle of minimum Renyi correlation as a counterpart for principle of maximum entropy and principle of minimum mutual information. We saw that in the continuous case, under fixing first and second order moments, jointly Gaussian is a distribution, and we learned the structure of distribution through that result. Then we went to the discrete case, and we saw that if there exists a separable structure in the distribution minimizing Renyi correlation, then that separable structure distribution would be a minimizer distribution under the class that we fix first and second order marginals. And then we provide an efficient way in order to compute the distribution, the conditional distribution minimizes Renyi correlation. Under that condition, and we provide a necessary and sufficient condition to check where it satisfies and how to, the size of that subset that it would be satisfied under. And last, we provided a justification and interpretation for group LASSO using principle of minimum Renyi correlation as an application to see how can it be applied to learning and modeling problems. So that's it.
Farzan, I have two questions. One question is that in this discrete case, for any first order, second order constraints, can you compute the minimum Renyi correlation? Or let's say under that condition?
Under that condition, we can compute, but it would be always a lower bound. So in that slide, I didn't go to details.
If that condition doesn't hold, you can still give a joint distribution, but actually
it doesn't minimize Renyi correlation, but it provides us with this lower bound on the value of minimum Renyi correlation, and that's why we had this justification for LASSO problem.
I see. Then the second question is that usually in practice, the statistics is you don't know the distribution. You need to estimate. But here is like you estimate the distribution, then you plug in this. But what we showed is like entropy, all other functionals, you first estimate, then plug in, and then optimize. In general, leads to something way far from the true stuff.
Yeah, sure. So for learning goals, let's say you want to do maximum a posteriori probability. So you need a conditional distribution. So from entropy or mutual information, you can do these goals. But because of that, we feel a need in order to estimate the joint distribution, estimate a distribution that we can achieve learning goals such as classification and feature selection under. So I think that for those reasons, estimating mutual information or entropy would not be enough. So for example, suppose a prediction setting, you want to make predictions and you need, for maximum a posteriori probability, you need the conditional distribution y given x. I hope that gives it.
Any other questions?
Yeah. So have you looked at beyond the additive structure assumption? What if it has some other non-linearity after the...
So basically what we need to do, let me go back to setting. So here we just consider these features x1 to xp. Now I can define some more features. Basically I can, for example, I have xi1, I can consider xi4, which is for x2, and then I may have the XOR of these two. I add it as a feature in my data set. And in this way, I can consider high-order interactions of xi's and how they can affect this y. So that's a way that we thought of in order to address this need. Yeah.
So in practice, often you have some labeled data and a lot of unlabeled data. Right, so the unlabeled data in your formulation can surely be used to say better approximate the marginals.
So yes, just question to get your question. Yeah, so are you mentioning the
y? So here for every row, in the picture here, for every row you know the value of y.
Right.
But often you'll have lots of rows where you know the x's but you don't know the y's.
Right.
Like you have the sequences of many people but you don't know whether they have cancer or not.
So we can use them in order to have a better approximation of the the xi's marginals. So we consider, for example, x1, x2 marginal. So we can use them in order to have a better approximation of them. But I think in terms of the marginals of y and others, they cannot be helpful. Yeah.
So my question was, they can be used to better approximate the marginals of x, but do you think that maybe slightly modifying the formulation or something you could potentially make better use of the unlabeled data?
maybe we can do prediction for those unlabeled data, and then we add to, I'm not sure about that, just it's an idea. Can we discuss about the offline? I think that would be an interesting idea.
Yeah, I was wondering actually if you can say anything about more general families of constraints, so not just on the first and second order marginals.
So now we are working on this problem. And specifically, we have shown that in classification problem, if you solve this distribution that minimizes Renyi correlation, we can have a very good bound on the maximum error that we can make in the prediction problem. But so far, the results that we have are just based on these second order marginals. But we can, I think, extend it to other cases. One way is to, for example, you can define features x1, x2, just concatenate these two x1, x2 together, make a new feature, and then add to this. So in this way, you can have, for example, third order and fourth order marginals. But still, we are limited to this marginals case. But that would be an interesting question to think about.
All right. Thanks again. Thanks.